Last time, we looked at insertion sort, an algorithm that thrives when your data is already mostly in order, neatly shuffling items one position at a time until everything lines up. Today, we are looking at algorithm number 3, selection sort. It belongs to that same family of simple foundational algorithms, but its operational instinct is the exact opposite. On paper, selection sort has a terrible reputation. It runs in quadratic time, meaning as your list grows, the time it takes to finish balloons exponentially. Yet it remains an essential tool in specific high-stakes environments. While it might be agonizingly slow to compute, selection sort possesses a highly specific superpower. It touches your machine's physical memory as little as physically possible. In standard computer science, we generally assume that all memory operations cost roughly the same. Reading a value and writing a new value are treated equally. But that assumption breaks down when you work with where-limited storage, like EEPROM or flash memory. In these formats, writing data carries a literal physical cost. Reading data from these chips is cheap and effectively unlimited, but every time you write a new piece of data, you physically degrade the memory cell, permanently shortening its lifespan. If you unleash a standard approach like bubble sort onto this hardware, it can perform massive numbers of write operations, constantly swapping items back and forth. That high write volume will literally burn out the physical drive. In an environment where every write pushes the hardware closer to death, computational speed stops mattering. Minimizing how often you alter the disk becomes the only metric of success. To achieve this, selection sort operates under one strict rule. It splits your list into a sorted region and an unsorted region, and it will scan the entire unsorted section before committing to a single swap. In Pass 1, it scans the 5 numbers, identifies 1 as the minimum, and makes one physical swap to the front. In Pass 2, it ignores the sorted one, scans the remaining numbers, finds 2, and makes exactly one swap to lock it in. By Passes 3 and 4, the next minimum values, 4 and 5, are already sitting in their correct slots. The algorithm recognizes this, skips the physical write entirely, and by default, the final element is forced into its correct place at the end. This visual tracks how that rigid, deliberate mechanism works across the entire list. The boundary dividing the sorted and unsorted regions marches exactly one position to the right after every single pass. The algorithm does all of its heavy lifting through cheap observations. It prefers to read the data thousands of times to guarantee it only has to physically move an item once. This creates an interesting mathematical profile. To find the minimum value every single time, it is forced to make a massive number of comparisons, resulting in a slow O of n squared time complexity. This chart contrasts read volume against write efficiency. While the dense orange bars represent the massive comparison load, the sparse purple bars prove physical writing is strictly linear. For n items, it performs at most n-1 swaps. We can see exactly how this mathematical limit is enforced by looking at the Python source code. The actual command to swap 2 items is pulled completely outside the inner scanning loop. The inner loop only reads data. It is structurally forbidden from writing. You might notice this specific implementation hunts for the maximum value and builds the sorted region from the back of the list instead of the front. The mechanical logic, however, is identical. By physically isolating the write command outside the scanning loop, the code guarantees it will execute the absolute minimum number of hardware-altering operations. Because of this specific design, you only deploy selection sort under strict conditions, when your embedded hardware limits your write capacity, or when you have absolutely zero extra memory to spare for temporary data buffers. You avoid it everywhere else. If you have large data sets, if you need equal values to maintain their original sequence, or if your data is already partially sorted, this algorithm offers no advantage and will only slow you down. Selection sort is a highly specialized tool, engineered for extreme physical constraints, solving a hardware problem through software design. The source code and structural concepts we've explored here are drawn from 50 Algorithms Every Programmer Should Know, an excellent resource for understanding how these foundational tools are built. But while selection sort solved the hardware problem, it completely failed to break the quadratic time barrier. To sort massive datasets quickly, we need to abandon O of n squared entirely. Next time, we look at algorithm number 4, merge sort, and see how it finally achieves O of n log n speed.